First things first, how's the sound? People
It's
hear
good.
me? I got a new microphone, which will hopefully address the echo problem. Let me know if the volume is good. We are picking up with what we started last time, talking about persistent data structures. We'll finish that and begin talking about splay trees in the later part of the lecture. So if you recall from last time, our goal is to make data structure operations persistent. And we defined two different types of persistence. Partial persistence is about being able to query the past. So you do some operations, and then you do some more operations, and then you do a query about what the state of the data structure was before you did some of those operations. We also talked about full persistence, where you can both modify the data structure and query it in the past, but those modifications have effects that propagate forward into the present. And so you're able to query what the data structure looks like, would look like now if you made these changes in the past. And we started talking about a general technique that will be applying to pointer-based data structures. Which means that they are a collection of fixed size nodes and those nodes can contain a constant number of scalar values, numbers or characters or whatever, and pointers to other nodes in the data structure. And many of the data structures that we work with are pointer-based data structures. Arrays are a very important exception because they grow unboundedly large and contain an arbitrarily large number of pointers and take advantage of that for indirect addressing. But many data structures fit into this model, for example, binary search trees and heaps, or Fibonacci heaps, for example. And so we're going to talk about a general technique to make the sort of atomic operations on such a data structure of examining a scalar or a pointer field from one of the nodes, or modifying one of those values or pointers. We are going to want to make those persistent. If we're able to do that, then the structure that is built from those nodes becomes persistent as well, right? So last time, we talked about one obvious method for making a data structure persistent, which is called the fat node method, where we replace each field by an array, and we store changes in increasing order of time. Right? So if we do this, after we've made t changes to the data structure, or to the field, what is the time for a lookup, to make a modification, to do a lookup in this array? If we're going to make a query about what the value of this field was at a particular time, how would we do that?
O of log t with binary search.
Right. So we do the lookup in order log t time using binary search on the time value. How long does it take to do a modification?
O of 1.
This is order 1, right? You just need to append a new value at the end of your array. But time is, sorry, so this is not terrible, right? So basically, if a pointer lookup now takes log t time instead of taking constant time, it means that we can perform all of the data structure operations with a log t slowdown overall compared to the underlying data structure. And we can perform modifications with no slowdown at all in the data structure, except that a modification often involves looking at things first, and the lookup part will be slowed down. But this isn't the only quantity that we're interested in our data structure. There's also the issue of space, right? This is an important issue in any kind of version control system, is how much space you're using to store all the different versions. So what's the space cost of making a modification? Actually, first of all, notice that lookups don't have any space cost because they're read-only. They don't write anything. But what's the space cost of a modification?
Like constant, right? It's not bad.
Again, it's order 1, right? And of course, this is optimal, right? If you're going to store a new value, you need space to store the new value, and that's all that we're using. Okay. So this is the most obvious method for versioning a data structure, and it's pretty good, but theoreticians are never satisfied. So we are going to look at an alternative approach. So let's consider a binary search tree. That looks like this. And suppose that I decide to insert another node into the binary search tree. Okay. Now, if I literally insert it like this, I've now modified the data structure, and I don't have a history. I can't look at what the data structure used to look like, right? But how might I preserve both the old version of the data structure and the new version of the data structure? Well, one brute force approach would be to copy the whole data structure, right? But also include the modification, right? So now I have the old data structure, and I also have the new data structure. And so if I put a time index on my copies, then I can binary search the time index to find out which copy to look at for a particular time, and then I can just use that data structure, right? So let's call this the copy method. And let's think about the cost of this. So what is the time cost of lookups using this copy the whole data structure approach? How much does that slow you down when it comes time to look up things in the data structure?
Will it become O of t? O of log t?
Well, there is an O of log t, but I claim it's not the same O of log t as in the previous fat node method.
of log t where t is the number of times you've ever made any modification as opposed to like modifying one node?
True. So it's a different t. Now it's the total number of modifications rather than the number of modifications to a particular node. So that's worse. But I mean, since log makes everything so small, it's not terribly worse, right? But it's also better in an important way, which is that this is an additive log t. Somebody want to explain what I mean by that?
You just need to find.
Once you
You just need to find t once and then just do anything you want with it.
Exactly. So in the fat node method, I was paying this log t for each pointer that I was looking up as I was walking through the data structure. But with this method, I pay the log t once to find the appropriate data structure root, but then I just use the regular data structure. So I add a log t instead of multiplying by log t. Okay. What's the modify cost though? Well, it's pretty terrible, right? If I have a size n data structure, then I have to copy the whole thing. And that's going to look like that's going to cost n. So it's going to be very expensive to modify. And the space cost is also going to be really huge. I'm generating a whole new data structure for each modification. But let's poke at that. Do I really need to generate a whole new data structure? I mean, one of the big insights in version control is that you work with diffs, right? So can I leverage that idea here?
Yeah.
Could you just represent it as like a pointer to the previous state and then like the change?
Yeah, so what has changed? Right? Or let me ask, what is the same between these two data structures?
Almost the whole tree.
Almost the whole tree is the same, right? So, shoot, this is going. Let's try another one. So, nothing at all has changed in any of these nodes, right? So there's really no need for me to bother copying these completely unchanged nodes. Okay. But what do I need to copy? Well, I created a new node. I need to make that. And if we think about it, when I created this new node, I updated a pointer to it. So I'm going to have to make a new copy of this node, right? But the other pointer in this node points to something that hasn't changed. So I might as well refer to it. Okay. Now if I back up to the root, well, the root points at something that has changed. So I need to make a new copy of that pointer and a new copy of the root node. However, the other pointer in the root goes to a node that hasn't changed, and so I might as well point to the unchanged part of the old data structure. So I've just reduced the amount of space that I used and the amount of time that I spend copying in a way that's really invisible to the usage of the data structure, right? When I am doing a lookup, I'm still going to do a binary search among the roots and find the appropriate root. And then I will follow pointers from the root. And I will not know whether a pointer that I follow goes to a node that was created as a copy or goes to a node that is unchanged from a previous time, right? The experience will be the same. So I still have an additive log t cost for lookups, but I'm getting the modification and space costs down. Okay. But not in a way that I can quantify yet, right? So for example, if this is a binary search tree, if it's balanced, then you can see that I'm only going to be copying log n nodes. And now I can sort of flesh out this notion of copying. What we're specifically doing is called path copying. Because what we're copying is the new node, or sorry, we're creating the new node, and then we need to copy things that point to it. We need to sort of work backward along pointers from that new node and copy things that point to it. And so this will, I mean, it might not be a path, but for intuition's sake, you can see that we're kind of copying back on the path to the root of the data structure. Does that make sense?
Wait, so we're copying nodes that are pointing to the nodes we modified?
Yes.
Okay.
Right? If a node only points to unmodified things, then we don't need to make a copy of it because it's not changing.
Then why is the root in this case being copied? Is it because it's
Right.
pointing to a node that was already...
It's because the notion of pointing to a modified thing has to be recursive, right?
Okay.
So this new node is added, and that means that the node that points to it is a changed node. But that means that the root is a changed node because it is pointing to a changed node. Okay?
Okay.
If we kept pointing the root at the old copy of the changed node, then we wouldn't see that change when we started from the new root. So that means we have to change the root, which means we have to make a copy of it. Make sense?
Yeah, thank you.
Sure. Yeah, keep those questions coming. All right. So if you think about it, fat nodes were nice because they had this very clear and small space bound for the modifications, but they had this multiplicative log t slowdown. Path copying was really nice because it had only a additive log t slowdown, but we can't really say too much about the space. So Sarnik and Tarjan figured out how to combine these two ideas of fat nodes and path copying. Okay, and they proposed a lazier path copying idea. So, you know, fat nodes are bad, right? Because of this excess space that they're using. But let's just consider plump nodes. A little bit fat. That's not a big deal, right? Most Americans fall in that category anyway. Their idea is to use plump nodes. And then if they get too fat, then switch to copying. Okay. And so I'm going to show you a method that works for tree structures. They generalize this to arbitrary structures. The nice thing about a tree structure is that only one node points at any other node. And I'm also going to focus on the partial persistence story, basically mainly because the notation is much simpler. But if you look at the Sarnik-Tarjan paper, you can see how this generalizes in a pretty straightforward way. So their idea for tree structures is in each node, we will make room for one extra time-stamped field. And we will use it for the first modification. Of the node. Okay. On the second modification, since there is no available field to store that modification, we will make a copy. And notice that that copy will have a new extra field. Okay. So already this should be making you think a little bit about Fibonacci heaps, right? The mark bit. Do something special, do something the first time there's a change, but after that, do something different. Okay. Now, of course, if we do make a copy, we're going to have to update the parent of the copied node. To point to the new copy. Okay, so, you know, initially I'll have a structure like this with an extra pointer to hold a modification. On the first, sorry, let me make it a little bit richer. Right, so here I have a data structure. Now, if I decide I'm going to add a node, my first step will be to use the extra field in a node in order to make a copy. Sorry, in order to avoid making a copy. But the next time I make a modification to that same node, right, maybe I add another child, what I'm going to do is now I'm going to make a brand new copy of that node that has both children attached. And because I've made a brand new copy of that node, let's see, how do I want to represent this? So, no, let's represent it like this. So what I can do is I can update the extra field in the root, right? The parent node of the node that I had to copy. Its extra pointer field can now be used to point to that copied node. Okay. So does this make sense algorithmically? We don't yet know what the consequences are going to be, but do you understand how this modification process works?
Just a quick question, like in the new timestamp field for the root node, would that also have to point to the left child?
Absolutely, right? So, no, sorry. The new timestamped field does not, but the root node has all of its, right? The root node has the original fields of the data structure plus one extra timestamped field. So the other fields still point at what they used to point to. We are just adding information to the timestamped field to represent this new thing, and which field we're overriding. So we will have a timestamp that says after time t, stop paying attention to this prior value of the pointer, and instead pay attention to this new value of the pointer for this field. Okay.
In the first diagram, do the two arrows come out of both come out of the left half of the node?
Exactly. Neither of the, we're not using the extra node, the extra field of the of any node actually. These we have null pointers in the leaf nodes, right? And we also have pointers to the two children, and none of that is using the extra fields. When we make our first modification, we modify one of the null pointers in the right child. Right, and so what's going to be indicated is that in the extra field we are going to record that we overrode the right child, and its new value is a pointer to this new node. Right, but on the next modification, because this extra field is full, we now need to make a new copy of this root, of this node, right? With again not using the extra field of the copy. Oops, hold on a sec. But that means we have to update the field of the root, the extra field of the root. In order to indicate that there's an override of the right pointer of the root. Clear?
Does the extra field only store one pointer?
Yes. If you change a left pointer in a node and then you change a right pointer in the same node, that's 2 changes to the node, and only one of them can fit into the extra field.
Okay.
So you have to make a copy at that point. And that's, I mean, this is a slight oddity of this extra field, is that you have to say which field it is covering. Okay? So if we do this, if we make modifications like this, what do the lookup steps look like? Right? So if we want to look up a particular field of a particular node at a particular time t, how do we do it?
Well, don't we have to like go down the tree? But every time we want to search, right, we have to check both what we were originally looking at and then also the extra field to see if that has been updated, and then just go down the tree recursively like that?
Exactly. So basically on each primitive node, we just need to check if the field was modified before time t, right? And if so, we use the extra field to get the value that we need instead of using the real field. Make sense? So how long is this going to take? What is this going to do? If like, again, this is the operation of looking up a field in a particular node. So if we do this, what is the impact on the data structure performance in doing a general lookup operation or a general operation, which may include modification, but let's focus on lookups. What's the effect on doing a lookup operation on the data structure as a whole? I mean, how much time does this take? This is order 1, right? So it's only a constant factor slowdown compared to just looking at a field. And so, roughly speaking, we only get a constant factor slowdown in looking up, in a general lookup operation in the entire data structure. Now, I said roughly speaking. How come? It's not quite, it's not only a constant factor slowdown. What do we still have to do?
We have to find the data structure, which is an additive log t.
Exactly. So this path copy, or sorry, this plump node method, right? It copies nodes all the way up to the root, but you're still going to need an array of roots by time, because in the rest of the data structure, you're sort of figuring out time as you walk through the different nodes of the data structure. Your binary search has kind of been spread out into the data structure as a whole to walk down through times. But each time the root is modified, it doesn't have a parent that you can modify or copy. So you have to keep all of the roots around from all of the changes that propagate all the way to the root. So there still is an additive log t in the start of the lookup, but afterwards, once you found the appropriate root to start with, walking the data structure is only a constant factor slower than the original data structure. So in terms of runtime, right, this replicates the benefits of path copying, that there's only an additive log t. But now we have to talk about space. right? How much space does a modification to a single node in the data structure cost us? Okay. Well, we're going to play the same trick as we did with Fibonacci heaps. We're going to do an amortized analysis of this using a potential function. So again, the point of a potential function is to kind of represent deferred work or deferred resources that we're going to need, but we've put off actually acquiring them. We've put off spending the time, right? And so we want a potential function that represents the amount of deferred resource consumption, which in this case is going to be space, right? So if we think about it, what is a data structure that has a lot of space for updates, right? While you think about that, remember that once we define a potential function phi, we can define the amortized cost of an operation as the real cost plus the ending potential minus the starting potential. And if we do that, then the sum of the amortized costs is equal to the sum of the real costs plus the final potential minus the initial potential. And that is greater than the sum of the real costs if the final is greater than the initial potential. So have you had time to think about what might make a good measure of deferred work in our data structure? In this case, we're thinking about space usage rather than time usage. Let me ask the opposite question. What kind of data structure is one where you have no worries and everything is looking good for you to do a lot of modifications without having to allocate more space?
None of the right nodes are, right halves are occupied.
Exactly. If you have a node where all of the extra fields are empty, you're in great shape, right? Because all of your modifications can go into those extra fields. So we've got a potential problem. We've deferred some work if extra fields are full. And that steers us to the appropriate potential function. Now, if you think about it, you know, having a full field is only a problem for nodes that you might still modify. And nodes that are back in ancient history are nodes that you aren't going to modify. So this motivates us to look not at all the full fields, but instead to think about what we call live nodes, which are nodes that are reachable from the current root. Okay. And now our potential function phi is going to be equal to the number of full live nodes. That is, live nodes whose extra field has been utilized. Okay. So if this is our definition of the potential function, what is the amortized cost of copying a node? Well, there's two cases to consider. One is, or of a modification. So one possibility is to consider the modification when the extra field is empty. Right? So if I decide to modify a node and it has an empty extra field, what is the amortized cost of that going to be?
Constant time?
It's going to be one, or it's going to be one, right? Because we create a full node, right? What is the amortized cost of modifying a full node?
the depth of
Well, so remember, here I'm asking about an atomic modification, right? That is a modification to a single node of the data structure. Because any modification to the data structure is a series of modifications of individual nodes.
The copy costs one, but also the node won't be full anymore, so is it free?
Exactly. So when I modify a full node, I create a new node, right? So this costs one additional real amount of space. But the old node, sorry, I point to the new node. I point my parent to the new copy. And presumably, I had to reach that. I reached that parent by walking from the root. But that means that the old node becomes dead, right? Which means a decrease of one in the potential. So the amortized cost is 0 for that node modification, right? And that means that a full update of a whole path, a path copying step, right? Well, it's just like cascading cuts, right? I modify some leaf. If I copy it, I modify the parent. If I copy that, I modify the grandparent. I keep working my way up. But all of that copying is free until I get to the very last node, the one whose parent I don't modify. That last node gets a full pointer, but it's the only node to get a full pointer. And that means that I'm paying only a constant. So the cost of a full update to the data structure is constant. And again, this is a space cost. So each time we modify the data structure, we only have to use one additional unit of space in an amortized sense. Sometimes when we're copying a full path, we're going to be using a lot of space in this operation, but it's averaged out over many previous operations where we filled the pointers that were copied, or filled the nodes that were copied. Does that make sense? Okay, so now we have a very powerful technique because this, this method allows us to spend only one unit of space per modification and get lookups which are only an additive factor of log t slower than the cost of using the original data structure. So for example, if I have a binary search tree and I make a polynomial number of modifications to that binary search tree, well, there's an additive factor of log n in the lookups, but I was already spending log n on the lookups, so my asymptotic runtime for this versioned data structure is just as good as the asymptotic runtime of a standard binary search tree. So that's pretty nice. Any questions about it?
So when you copy a node, do you copy all of its children, or do you just
Nope.
copy that node?
Nope. I mean, if you think about the algorithm I described, right? You start at the bottom of the data structure. You've got a leaf, and so you think about that leaf. You change that leaf. Maybe you copy that leaf, right? That causes you to make a modification to the parent. But you make a separate decision about whether you're going to fill that parent's extra node or whether you're going to copy that parent. So sometimes the leaf change will propagate, and sometimes it will cause another copy, and sometimes it will not.
What happens if we change a parent node then?
Well, it's the same. So copying the leaf will force us to change the parent node. So now the parent node has changed, so we need to look at the grandparent. Either we need to fill the grandparent's extra field, or else, if it's already full, we need to copy the grandparent. So it may happen that you copy all the way to the root, and the actual space cost of this operation is very high. But the amortized cost of the space operation is constant. All right, so it's nice to have that general purpose technique, but to make it real, to make it interesting, for my next trick, I'm going to show you an application of this persistent data structure. It's an application to something which is called planar point location. And so planar point location is one of the canonical problems in the subdomain of algorithms known as computational geometry. And this is a field that we will be spending some more time on later on in the course. But what fundamentally differentiates computational geometry is that it's looking at problems involving points and lines in space or in the plane or in space, and it ignores the algebra that you need to actually compute and just talks about things like intersections, you know, finding the point of intersection of two lines, or asking about whether whether a point is on a line or which side of the line it is on, or asking about the length of a segment. And you just assume that you have access to these sorts of computations as primitives, just like addition and subtraction of numbers in our traditional computational model. Okay? And this is actually a pretty powerful assumption because, for example, the length of a segment might be an irrational number which we can't even store in a computer. And of course, you have to deal with that in practice, but we know how to deal with it, and so we just wrap that up and hide it inside of this more powerful primitive operation. So what we're going to be looking at in this particular computational geometry problem is a planar subdivision, which is just a division of the plane into a collection of polygons. Some of the lines may be infinite, who knows, doesn't really matter. Some of them might be finite, but the point is that you got a bunch of lines, they intersect in various places and create the vertices of polygons. And now you get a query point. Right? Somebody specifies a particular point, and the question is, which polygon is it in? Okay. So, for example, you know, when you click your mouse in a web browser, the browser has to decide which element of the display you clicked on. Did you click on this button, or did you click on this slider, or did you click in this text box? Right. So these are polygonal regions of your screen, and the browser needs to know where you clicked. So it's a pretty natural problem, and in fact, you've always seen the 1D version. So what's the 1D version of this problem? So now instead of having a plane, I've got a line, and I can imagine a linear subdivision where I specify a bunch of points, which breaks my line up into segments. And here too, I can have a query point and ask which segment is my query point in? So how would we answer that question?
Binary search.
Yeah, binary search, right? So the quote data structure for this problem would just be a sorted list of the endpoints, and I could use binary search to answer the which segment question in order log n time. So is everybody clear on the problem statement? All right, so let's start looking at a solution. And so let me make another planar subdivision. Yeah, that looks reasonable. All right, so one of the tricks that's often applied in computational geometry is a kind of dimensionality reduction, where you take a look at a two-dimensional problem and figure out how to think about it as a collection of one-dimensional problems. Okay? And the way I'm going to do that is I'm going to take all of the vertices and I'm going to draw vertical altitudes through the different vertices of the planar subdivision. Okay? And I claim that if I use these altitudes, whoops, I missed one. If I use these altitudes to divide up the problem, then I've made myself a collection of easy problems. I've turned this one hard problem into a collection of easy problems. So given these altitudes, how might you go about answering a planar subdivision, answering a point location query? Well, an obvious first step is to ask which slab, right? These altitudes create a bunch of slabs, vertical slabs of the geometry. What about in the given, once I have figured out which slab I'm in, how can I figure out my location within the slab? Right, so if we consider this slab over here, if I have a query point in here, right? I mean, visually I can see where it is, but computationally, what sort of questions might I ask in order to decide which polygonal region the query point is in?
You can query whether it's
line
above.
segment.
Sorry, I got some simultaneous stereo.
You can query whether it's above or below a certain line.
Yeah, we can do a binary search on the segments. Right? The key question now is, am I above or below a particular line segment? Right? And that again is a canonical primitive operation that you can invoke in computational geometry. It's not hard to figure out what the algebra is, but we don't even care. All right? So once I'm in this slab, I'll ask, you know, is the query point above or below this line segment? Okay, it's above this line segment. So is it above or below this line segment? Okay, it's below this line segment. These two line segments are right next to each other. There's nothing between them. So now I know the region of the query point, right? And the reason the slabs are so important is that it makes this notion of above and below completely unambiguous, right? You could imagine if I didn't have the slabs and I asked, you know, about above or below with respect to these two different line segments, well, they kind of cross each other. So there isn't a consistent ordering of those line segments that I can use for binary search. But within a particular slab, since there are no crossings, there is a total ordering on the line segments from top to bottom. And I can use binary search on that total ordering in order to find the query point. Does that make sense?
Quick question. Does this need pre-processing, finding those segments?
Yes. So I was talking about the data structure existentially, but now let's talk about the cost of this data structure, right? So we have two costs, right? We have a build cost and a query cost, right? So let's start with the query cost. Right? If I have this data structure, right? If I've got, you know, an array of slab boundaries, and within each slab, I've got the line segments of that slab in the proper order, what's the runtime going to be to find a query point? How fast can I figure out which slab I'm in?
O log n if it's sorted.
Right. So which slab is order log n? Once I've identified which slab, how long does it take me to find the region?
Also log n.
Also order log n, right? I'm just doing two binary searches. So the overall query complexity of this data structure is order log n, which is wonderful, right? We can do two-dimensional point location using two binary searches, just like we can do one-dimensional point location doing one binary search. And surprise, surprise, you can do three-dimensional point location doing three binary searches, and so on. But the query complexity is only part of the problem, right? What about the build complexity? So this is much harder. And actually, even before we get to the time, let me ask how much space this data structure is going to use. Okay, I'll bring the picture back over here so you can think about it. Right? Forget about how long it takes me to build it. How much space am I going to need to represent the result?
Something comparable to like the number of vertices times perhaps the number of line segments or the number of edges.
Number of vertices times number of edges?
Well, so you're going to have, so the number of slabs is going to be proportional to the number of vertices. So you need that, at least that much of space. And then for each slab, you need every intersection of a line segment with that slab.
Very good. Very good.
There's a question of like the properties of the graph that bounds it above or below, but like, who knows?
Right. So in the worst case, you're looking at something like vertices times segments, right? And I mean, I'm not going to go through the details, but you should be able to pretty easily come up with a sort of an n squared there, even if you only have n segments in the data structure and n vertices, right? If I make something like this, but then I put a whole lot of line segments above to all get broken by all of my vertices, right? Then it's going to be n squared space. And that's way worse than the linear space that we get from a binary search tree, right? So the question is, and of course, if the space is n squared, then the time's going to be at least n squared because you have to at least write down the data structure. So to avoid this problem, we bring persistent data structures to the rescue. So what we're going to do is we're going to go back to our picture and our slabs. with all of the vertical line segments representing altitudes that define the slabs. But now, instead of thinking of this as my usual X and Y coordinates, I'm going to think of the horizontal axis as time, t. Okay. And again, this is a method known as a sweep line method in computational geometry. I'm sort of imagining that I'm starting with a line at -infinity and sweeping it forward over time to investigate the structure that I'm looking at, or to build the structure that I want to create. Okay, so there are these various times. Okay, and what I want to ask about is, if I'm focusing on a specific time and moving a sweep line through time, what does that sweep line see at any particular time? Well, the sweep line sees intersections with some of the line segments, right? If my sweep line is over here, it's only going to see this segment. Earlier on, it saw all three of these segments, right? Now, as this sweep line moves to from left to right, various changes happen in what it sees, right? The intersection points the intersections with the sweep line, they do change coordinates. Right? As the sweep line moves to the right, this intersection point is going to move downward. Okay? But that's a number. And again, in computational geometry, we don't care so much about the numeric values. But at certain points, there are more significant changes than just a numeric change. There are actual topological changes. So what kind of changes can we see happening as we move this sweep line across time?
Some lines go from being above another to being below another one.
Exactly. So there are crossings, right? So at this point in time, this line segment is crossing this line segment, right? What about at this point in time? What's happening here? Well, it's harder to see, but these are not line segments. Here we have a pair of segments ending, right? They disappear, and a pair of new segments appear. Right? Here we have two segments disappearing while one continues. Okay? So the other kinds of changes are segments that appear, vanish, or cross. And where do these changes happen?
The vertices?
They happen at the vertices. And of course, we've already said that at each vertex, we're going to draw one of these altitudes. Okay? And that's the only place that there are topological changes. Inside of every slab, there is no topological change, which is exactly why we like the slabs. It makes it easy to do the vertical binary search. And you'll notice that also at each of these vertices, the number of changes is small, right? We get a couple of lines arriving, or a couple of lines disappearing or crossing. So what we're going to do is we're going to use a persistent binary search tree on the segments hitting the sweep line. Right? At a vertex, we're going to have some inserts or deletes or swaps. Okay. But what we know is that if we use a persistent search tree, these modifications are cheap. Okay. So for example, let's consider using a red-black tree. So one of the standard balanced binary search trees that you've studied, right? It's kept balanced. And it has a red-black bit per node. If you learn a different balanced binary search tree, you can use it instead, okay? But the balance means that the depth is order log n. So let's imagine that we move this sweep line from left to right. Each time we hit a vertex, we do some inserts and some deletes and some swaps of segments based on their order. Each update is done to a persistent red-black tree. And so what is the cost of each update? Well, we need to think about time and space, right? So how much time does it take me to do an insert or a delete or a swap in a persistent red-black tree? Well, I have to take that, I have to look at the number of primitive node changes, right? Because what we know is that each node change costs me a constant amount of time and a constant amount of space. Actually, I don't need to distinguish, well, I'll come back to that, right? So how many primitive node changes are there when I insert something or delete something or reorder something in a red-black tree? Right. How do you do an insert in a red-black tree? Maybe nobody's seen red-black trees.
One moment, let me pull up the book.
What was that?
Okay. Insert should take all of log n time.
How come? What are we doing? Well, we start by doing a regular insert.
Yeah.
Right. And then we walk up the path, rebalancing the tree. Which means that we may change the red-black bits, and we may rotate certain tree nodes, right? And each of those actions, a change of a bit or a rotation, involves a constant number of pointer changes, which from a persistent data structure perspective represents a constant number, right? It means that we're going to spend a constant space and constant time, okay? But since it's a balanced tree, there are only order log n such changes. And that means that we're going to use order log n time and space in order to do an insert into a red-black tree. The same is true of a delete and the same is true of a swap, okay? And so this analysis applies equally to time and to space. Okay. So now the question is, how many of these updates am I going to do as I sweep this line across the data structure?
The number of vertices?
Roughly the number of vertices, right? We have to be a little bit careful because the way I drew it, I actually allowed sort of three edges to collide in the same place. So we have to be a little bit careful of our accounting, right? But if you think about it, at a particular vertex, right, why do I have a vertex? Well, either a line segment is ending, or a line segment is beginning, right? Or there is a crossing happening. But a crossing you can think of as breaking a line into a pair of segments, right? So I can certainly ascribe each change to a particular segment, right? At every vertex, there is either a segment ending or a segment beginning. So the number of updates is going to be equal to the number of segments in that case, which is sort of the size of the input problem, which means that the overall cost of performing all of those inserts and deletions over time is going to be n log n operations times the log n cost per operation. Yes? Now, once I've done this, okay, what do I have to do in order to actually look up the location of a point?
I mean, you would look for, so you would find the update associated with it, which is basically finding the which horizontal segment, and then you would just go down the tree.
Exactly, right? Remember that the x-coordinate is time. So when I'm asking which slab, what I'm really asking is, what time was it when what was the time associated with this query point? And then I just need to query the slab associated with that time. So I'm just doing a persistent data structure lookup. And as we already saw, the cost of this is order log n to find the appropriate time, plus order log n to walk through the persistent data structure at the appropriate time. And so it's an order log n time lookup. Make sense? So this is pretty fantastic, right? It takes me n log n time to construct the data structure, and it uses n log n space. And once I've built it, it only takes me log n time to do a lookup. So it's just as fast as the one-dimensional problem asymptotically, and it only takes me n log n time to build that data structure in the first place, which is pretty close to linear. Now we can do one little refinement on this. If we really look at red-black trees, if you go back and look at how red-black trees work, on a particular insert or delete operation, red-black trees modify possibly log n bits, but they only do one rotation. Again, they're kind of like Fibonacci heaps, right? You cascade the cut up and eventually you set a mark bit. So similarly with red-black trees, you walk, after you've done an insert, you walk back up the tree, fiddling with the red and black bits. And when you find that you need to do a rotation, you perform that rotation, but then you stop walking up the tree. So you only ever do one rotation. Okay. So, the other thing to notice is that we don't care about the historical red-black bits. Those bits are only relevant to doing rebalancing. They don't matter for doing queries. So we don't need to persist the red-black bits. We are only going to persist the rotations. And since there's only one per insert or delete, that improves the space usage to 1 per insert or delete. And that means that the space of the data structure improves to order n instead of n log n. So in fact, this data structure is perfect. Space is order n, time for construction is order n log n, and I claim you can't do better than that. And the query time is order log n, and again, I claim you can't do better than that, right? Why are these optimal runtimes?
Can probably be mapped to sorting, the first constructing thing.
Yes, in fact, I mean, we really just kind of talked about it. These runtimes are optimal even in 1D, right? Because in the one-dimensional version of the problem, right, building the data structure basically involves sorting the points, and querying the data structure is basically binary search. And those two things are optimal for information theoretic reasons. So that's the end of the story of persistent data structures. Okay? Any questions about it?
Could you generalize this to a n-dimensional problem?
Yes, this has a generalization where it takes you d log n time if you are working in a d-dimensional space to do a query. The construction is basically linear in the complexity of the arrangement of geometric objects, which can get quite complicated in high-dimensional spaces because lots of things can intersect lots of other things. But this data structure is optimal for the given complexity.
One little question. Was n the number of vertices or the number of segments?
It's actually, well, so it's the number of segments. Notice that in order to have a vertex, you have to have a segment. So there are going to be asymptotically more segments than vertices. Anything else? All right. Two things I wanted to mention quickly before I give you a little intro to splay trees, which will be our next topic. First of all, if you don't want to get stuck in the waiting room, if you sign in using an MIT or Harvard email address for your Zoom account, you'll be passed right through without having to go through the waiting room. Another thing I'll mention is that I'm going to be putting up a survey of background knowledge to help me figure out whether there are certain things I need to teach or whether there are things that I can take as given that you know. So keep an eye out for that survey. Okay? Any other questions before I introduce our next topic? Nope. All right. So our next topic is splay trees. And these were developed by Slater. And who do you suppose developed them with Slater?
Tarjan.
Tarjan, of course, because Tarjan is the god of data structures and invented all the good ones. Splay trees are a particular kind of binary search tree. And we know all about binary search trees. Binary search trees are great if they're balanced, right? If we can keep them balanced, we can do search, insert, and delete, all in order log n time if we're balanced. And therefore, people have come up with a tremendous variety of ways to balance binary search trees. There's red-black trees, there's AVL trees, there's scapegoat trees, there's 2-3 trees, which aren't really binary trees, but are close enough. It goes on and on, right? And the goal of all of these search tree data structures is to keep the tree balanced so that all of the basic operations of search, insert, and delete run in order log n time per operation. And all of these are kind of annoying because you have this hassle of tracking extra info and doing specific work to maintain those extra bits or colors or balances or whatever else that you use to actually do the rebalancing, right? So Slater and Tarjan developed what they call self-adjusting binary search trees. And this is from 1985. And I mean, Fibonacci heaps are a pretty cool data structure, but self-adjusting binary search trees are absolutely astounding. They're probably one of the coolest data structures ever discovered. What's amazing about them is that they keep no balance information at all. All you have is a bare binary search tree. No bits, no 2 3s, just no size, no counts of sizes of subtrees. All you have is the binary search tree. And as a result, it's not even balanced, right? Just like the Fibonacci heap, a binary search tree can end up looking, these self-adjusting trees can sometimes end up looking like linked lists, okay? Nevertheless, they only take order log n time per operation in an amortized sense. So because they are balanced, because they are not balanced, some of your operations may be very slow, but if you amortize over all the operations you perform, these are just as good as regular binary search trees. In fact, they're way better. They outperform regular binary search trees in formalizable ways. Okay, so for example, if you search for all of the keys in your tree in order, then a regular binary search tree will take you n log n time, but a splay tree will do it all in n time. It somehow knows that this is an easy sequence of searches, and it does them faster. Okay. It also has more operations than a regular binary search tree. You can merge 2 splay trees in order log n time, and also split them into 2. And there are a number of other very powerful operations that you get for free in these self-adjusting binary search trees, even though they have no auxiliary information at all.
Is split also O of log n time?
Yep, split is basically everything is order log n except when it's faster. They're incredible, these data structures, these trees. Now, the incredibleness of the data structure, the way you pay for that is in a much more sophisticated analysis. And there's some real cleverness and arguably even black magic in figuring out how to prove that this data structure actually does what it proposes to do. It uses a potential function. And instead of keeping the tree balanced, it uses a potential function that measures the imbalance. And it proves, in the standard potential function sort of way, that you need many inserts to cause an imbalance. And they then show that the searches decrease the potential and are therefore paid for even if there is an imbalance. Okay, so a very magical data structure that we will spend next lecture on, where the structure itself is incredibly simple, just a plain old search tree with no extra information at all. And all of the cleverness is in this sophisticated potential function analysis that shows that if you do the right operations on this tree for insertion and search, then everything is fast. So any questions about that introduction? We'll dive into all of that next lecture.